Okay, so welcome everybody. Thanks everybody for joining and for listening today on Zoom. Unfortunately, better to be in person, but unfortunately here we are. So yes, so this is just an online presentation given by it will be given by Nick Clemett today, but these are a series of presentations that we've been doing between different researchers in Pavia that we decided to share online and hopefully get some discussion and input from other people as well. Just a brief note, some things to bear in mind during the meeting. So we will have just a presentation as usual, and then some time for questions and comments later on at the end of the presentation. So I would ask everybody to keep their microphones off, cameras on, off as you wish. I will be recording this meeting, so it'll be available online as well. So there's no problem there. So you can go back and have a listen through again if you miss something. But everything will be available, and also the slides as well. So the presentation today will be given by Nicholas Clemett. Nick is a researcher at IUSS Pavia and University of Pavia. So he's been working here for quite some time now, and the presentation is going to be on the optimal seismic retrofitting of existing buildings considering the environmental impact. So I don't want to give too many spoilers away, so I'll just let Nick introduce the work and give us what I'm sure will be a great presentation. So take it away, Nick.
Yeah, thank you very much, Gerard. So yes, as Gerard said, my name is Nick Clemett, and I'm working at the moment with IUSS Pavia and the University of Pavia. And I work very closely with the team of Ricardo Montero, Gerard O'Reilly, Wilson Catafilis, and Giameria Gabinelli. And today I'm going to be discussing or talking about some of the recent work we've been doing with a focus on the optimal seismic retrofitting of existing buildings considering environmental impact. I'm going to start this presentation by talking a little bit about our motivation and the aims for this study. We're going to talk a little bit about what environmental impacts are and life cycle assessment. I'm going to introduce you guys to the multi-criteria decision-making procedure that we use to perform our optimal retrofit selection. And then we're going to apply these concepts to a case study structure and actually go through the process of implementing our optimal retrofitting selection framework. And then we're going to finish up by discussing some of the conclusions of this study and possible future research opportunities. So, as most of you are probably aware, a significant portion of the European building stock, and particularly buildings in Italy, were constructed following World War II. And this was typically done prior to the introduction of seismic codes in the 1970s. And as a result, many of these buildings actually lack many of the typical details that are characteristic of modern seismic resistant design. And this leads to the buildings being susceptible to seismic damage during earthquakes. And this poses not just a risk to human lives, but also the possibility of significant economic losses following an earthquake event. So obviously we want to try and improve the performance of these buildings. And there's a couple of ways we can do that. Typically, we can either demolish our deficient buildings and replace them with code compliant seismic resistant structures, or we can retrofit them. Typically, demolition and replacement is not the preferred option, given that it's high capital expenditure and the extended interruption that both residents and businesses occupying these buildings would face if it was to be demolished and replaced. But additional to these, there are also significant environmental concerns associated with demolition and reconstruction. Within a European context, the building sector is responsible for approximately 40% of the total energy use and greenhouse gas emissions of the European Union. Now, admittedly, most of this is actually associated with the use phase of a building's life cycle and not specifically with construction and demolition. However, approximately 10% of these emissions are related with the construction phases. So this is not an insignificant amount of emissions that we're talking about. As well as greenhouse gas emissions, construction and demolition also produces a significant amount of solid waste, approximately 800 million tonnes a year, and that's equivalent to almost 30% of the European Union's total solid waste production. So you can see that given these numbers, as well as the significant costs associated with demolition and replacement, it's easy to see why retrofitting tends to be a preferred option when looking to improve the seismic performance of our structures. So given that we've decided to go down the retrofitting path instead of demolition and replacement, there's a number of options for decision makers and engineers. These revolve around the particular retrofit strategy that you're going to take. Are we looking at local strengthening techniques? Are we going to be adding new lateral load resisting elements or trying to reduce the seismic demands acting on our structures? And there's also an array of different retrofitting techniques that can be used to realize these different retrofitting strategies, such as FRP wrapping and concrete encasement to increase local strength and ductility capacities. We can add reinforced concrete shear walls or braced frames as our additional load resisting elements. And we can utilize viscous dampers and base isolation as well to reduce the seismic demands on our structures. So given this wide range of options, how do we actually choose which one is best for our particular situation? Well, over the years, there have been many methods that have been proposed to sort of answer this sort of question. And historically, most of these have focused on only structural or economic parameters. Some work that our research group has recently carried out compared the rankings obtained using a range of these different selection methodologies. And we found that the rankings obtained varied significantly depending on what method was used. And it was observed that simplified methods based on economic parameters, structural parameters, or a combination of both were typically unable to produce rankings similar to more comprehensive methods that incorporate a range of economic, social, and structural parameters as well. And that's not to mention environmental variables, which is the purpose of this study. Our previous work recommended that a comprehensive method like the multi-criteria decision-making would be a better option when trying to select an optimal retrofitting solution because of its ability to incorporate a broad range of decision variables. And this is particularly important given that consideration of a building's environmental impact is becoming far more common as the building sector is the target of many national or transnational emissions reductions policies, as well as clients are just generally more interested in trying to achieve green building accreditations. It's well established that seismic hazard has an effect on the environmental impact of structures. And in the past, a number of studies have looked at different variables that can be used to describe the environmental impacts associated with seismic hazard. And some of these include the expected annual environmental impacts, environmental cost-benefit analyses, or total life cycle environmental impacts. As far as most of this literature is concerned, it pertains particularly to the assessment of hypothetical new build structures, and very few studies have actually focused on the environmental impacts associated with retrofitting existing buildings. And prior to us beginning this work, to the best of our knowledge, there were no studies in which the environmental impacts associated with retrofit alternatives were included within a comprehensive decision support framework to facilitate the selection of retrofit alternatives. So tying all of this together sort of leads us towards the aims of this study. And they're the first one being to investigate how environmental impacts can be considered in the selection of an optimal retrofit scheme for an existing building. And then building on that, we want to investigate whether or not the inclusion of these environmental impacts will actually affect the choice of our optimal retrofit solution. So now I'm going to talk a little bit about environmental impacts and life cycle assessment. So environmental impacts occur when waste products and emissions associated with industrial processes and resource use are expelled into the environment, and they will forcibly alter our environment in some way. Now, some classic examples of different emissions that impact our environment are the methane produced from agricultural processes, nitrogen oxides from the use of combustion engines, and carbon dioxide can be produced from, say, steel manufacture and production as well. And the environmental impacts are the different ways that these emissions can alter our environment. And they include things like acidification potential. So how likely is a particular emission likely to induce phenomenon like acid rain? They also include things like ozone depletion. And probably the most famous and well-known of all is greenhouse gas emissions or climate change potential. Generally, we talk of in terms of environmental impacts as a way of trying to simplify the effects of thousands of different types of emissions into a relatively small group of variables, which allow us to then compare the different, say, levels of environmental friendliness between different products that have different emissions profiles. In this particular study, from now on, when I refer to environmental impacts, I'm going to be specifically talking about the climate change potential. And the reason that I'm doing this is studies have shown that the climate change potential can be used as a proxy for pretty much all of the environmental impacts that you would be concerned with, because there's a positive correlation between these, and that effectively means that when our climate change potential value increases, it's highly likely that all of the other environmental impact metrics are also going to increase to some degree. So from now on, when I talk about environmental impacts, you can think of it as climate change potential, or say greenhouse gas emissions measured in terms of kilograms of carbon dioxide equivalents. So now that we know a little bit about what an environmental impact is, how do we actually calculate that? And that's where life cycle assessment comes in. The life cycle of a building can generally be divided into 5 main life cycle stages, like the ones that you can see here in this figure. So raw material extraction, material manufacturing, construction use, and end of life. And the goal of a life cycle assessment is to estimate the environmental impacts associated with the processes that occur during each life cycle stage. For clarity, environmental impacts occurring in different parts of the life cycle tend to be given different names, as you can see highlighted in the figure here by the different colored dashed lines. So for example, all of the processes encompassed within the blue dashed line are related to pre-use, or called pre-use embodied impacts. And they're the embodied impacts that are incurred up until the completion of construction of the building, prior to it coming online and starting its useful life. Conversely, the operational impacts are the environmental impacts that are generated during operation of the systems within the building the heating, the cooling, the lighting, and the energy use, for example. And things like the recurring embodied impacts, shown in red, are the impacts related specifically to the structure that occur during a building's life cycle. So they're things like structural maintenance and retrofitting. You can think of as embodied impacts as being specifically related to the structure. And for the purposes of this study, that's what we're going to be looking at. We're going to be looking at the embodied impacts. Encompassing all of the different types of environmental impacts, we have our system boundary. Now, this is effectively a line that you can draw around your study, which identifies which processes will be included in the study and which will not. And in this case, you can see that the black line specifically excludes the operational impacts here. This system boundary is a really important thing to consider, particularly when you're going to be comparing results from different life cycle assessments. If the system boundaries are different between the two assessments that you're trying to compare results for, you're effectively trying to compare apples with oranges, and it's something that doesn't, it's not going to work particularly well for you. So once we've outlined our system boundary and we have identified all of the contributing processes, the next step is to then calculate the environmental impact. And there's two methods to go about doing this. The first one is our process-based life cycle assessment, or process-based life cycle inventory. And effectively, this is what I've just been talking about. We develop a list of all of our processes that contribute to the life cycle of the building. We identify all of the output emissions expressed in terms of emissions per unit of product produced. So for example, kilograms of CO2 per kilogram of steel, or kilograms of methane produced per kilogram of steak that arrives on my plate. And then once all of this is being done for every single emission and every process, the results then get converted into the environmental impacts that we've talked about previously, using some well-established conversion factors, such as those from the United States Environmental Protection Agency's Tracy tool. Once we've done that, we take a detailed bill of materials for the construction of, in this case, our building, and then we can multiply the required material quantities by the environmental impacts per kilogram of material and obtain an estimate of our environmental impacts. Now, this process-based life cycle assessment is a bottom-up procedure, and it's considered to be the most rigorous method for performing a life cycle assessment. However, it is incredibly time-consuming for complex systems such as buildings, and it can also be susceptible to truncation bias, which occurs when key processes are left outside of the building scope and not considered in the analysis. And sometimes this error can be as high as 30 to 50% of the total environmental impact. So that leads to an underestimation of the total environmental impact. The second main method that we have for determining the environmental impacts is an environmentally extended input-output life cycle assessment. And this is a top-down method based on modified and economic input-output tables, which effectively model economic transactions between different sectors of the economy. So what these input-output tables effectively do is they tell you how many dollars one industrial sector of the economy spends in each of the other sectors in order to produce $1 worth of its own product. And some examples of the sort of industrial sectors I'm talking about are production of lime and gypsum products as a sector, production of metal structural products as an example of another. We can modify these input-output tables using industrial emissions data so that we can add some additional lines to them that effectively tell us the environmental impacts that each sector produces per dollar of product produced. And then once we have this, we have a very useful tool for estimating our environmental impacts. And the steps are reasonably straightforward, and they're highlighted here in figure 5 in the bottom right corner. Effectively, all you have to do is develop an itemized cost estimate of the building. And then for each line item, you proportion the cost estimate between the different industrial sectors in your economic input-output tables. And then you sum the total costs spent in each industrial sector across all of the line items. So that's effectively summing down the columns here and getting total values. And then you multiply these total costs by your environmental impact factors for each sector, and you have your total environmental impact values. Unlike the process life cycle assessment, this method does not suffer from truncation bias because it incorporates all of the aspects of the economy implicitly in the model. However, it does have several sources of its own error, notably aggregation error, the homogeneity assumption, and the fact that environmental impacts are going to vary linearly with cost. Because of these reasons, it's not considered to be as rigorous as the process-based life cycle assessment. However, it is generally accepted as a useful method for providing comparisons between different design alternatives. And as a result, this is the method that we've adopted to take on further in this study. We'll just take a little bit of a step back now and see how we can look at how the environmental impacts of our retrofit installation and the repair of our seismic damage fit into the life cycle of a complete structure. You'll note from the previous figures that the retrofit installation and the repair for seismic damage was shown as single processes occurring during the use phase of the building's life cycle. Now, it's important to remember that actually each of these processes have their own mini life cycles as well, and the scope of these processes must be also considered and defined. So if you look at this figure here, you can see different boundary systems that we're going to consider in the different for the different types of environmental, or at the different times we have to estimate the environmental impacts throughout our study. In general, when estimating our environmental impacts, we have not included the effects of the environmental impacts associated with labor. And for the most part, we're also not considering the environmental impacts associated with transportation. The reason for this is that transportation is a very sort of location dependent variable, and you need very specific data to be able to actually estimate it effectively. And we've made the assumption in this study that because we're looking at a sort of comparative assessment, if we assume that the transportation environmental impacts are going to be similar between each of the retrofit alternatives, then overall, excluding them from the analysis is not going to alter the results too much. If we take a look at this figure now, you can see the red boundary. This outlines the system where we're going to consider the repair for seismic damage. So effectively, we're looking just at the raw material extraction and the raw material and the material manufacturing processes. We don't account for any end of life processes with the in the repair stage, because we make the assumption that when we're repairing the structure, we're not adding any additional value to the structure, so we don't need to account for any extra end of life projects. In contrast to that, the green boundary, which models the installation of the retrofit alternatives, encompasses the raw material extraction, material manufacturing, and also the end of life factors. And that is because when you retrofit a structure, you are typically adding additional elements to the structure, and the new materials result in increased materials that need to be disposed of at the end of the building's life cycle. The blue boundary represents the environmental impact calculation for building replacement that we use in our peer PBE assessment procedure. And in this particular case, we do include the construction environmental impacts for transportation and labor. And that is because when we calculate this value, it's a very rough estimate. We use the replacement cost of the building and multiply it by the environmental impact for a single industrial sector for school and vocational buildings. And that just gives us a rough estimate of the environmental impacts for school and vocational buildings, as I mentioned. And then the fourth boundary you can see here is our black boundary. And this is the system boundary for the total life cycle of the complete building. And effectively what this is the union of the three other system boundaries that I've just described, and also the environmental impacts associated with structural maintenance. The final point that I would like to mention in relation to the life cycle assessment is how we estimate the environmental impacts associated with seismic damage. I hinted at this before in the previous slide, and it's related to our peer PBE framework. As most of you will likely be aware, this framework is not actually limited to the classic deaths, dollars, and downtime. And in fact, any variable of interest can actually be used to describe the performance of our structure, provided that a set of consequence functions can be developed that relate the different levels of observed damage to the corresponding values of our variable of interest. So if we consider our environmental impact values, we effectively just have to develop consequence models in exactly the same way we would for economic losses, and then we perform the peer PBE assessment in exactly the same way we normally would. So as you would expect, the sort of results that you get out are things like the environment, a certain number of environmental impacts given a particular intensity event occurred, or the more classic time-based results such as expected annual environmental impacts. We're going to change gears a little bit now, and we're going to move on to talking about our multi-criteria decision-making procedure. This is a very nice procedure, actually. It consists of 6 key steps to identify an optimal solution. The first step is, first of all, identifying the key decision variables that we want to evaluate. And an example of a set of suitable variables is shown in the table 1 on the right-hand side of the slide. And these are, in fact, the 13 decision variables that we use in this study. They encompass a range of economic, social, and environmental variables. And in this instance, we've explicitly included 3 different types of environmental impact decision variable, particularly the installation environmental impacts, C9, the expected annual environmental impacts, C10, and the environmental impact life cycle performance metric as proposed by Caruso et al. In C13. We also obviously have our typical installation costs and maintenance costs as well. The second step in this procedure is determining the values of the weight vector. Now, this is an important step because it effectively indicates the relative importance of each variable to the decision maker. You can obtain a weight vector in these types of studies in several different ways. You can use mathematical procedures like the analytical hierarchy process, or alternatively, as we've done in this study, you can leverage the results from surveys from people experienced in the field of seismic retrofitting. So what we did is, in one of our previous studies, we conducted a survey and asked a number of experienced professionals to rank how important they felt a range of different variables were. And after post-processing and normalizing the results, we were able to obtain a weight vector to be used in these sorts of studies. The third step is compiling the decision matrix. And effectively, all you do here is identify the values for each decision variable for each alternative. In the decision matrix, the variable in position D1 is simply the value of decision variable 1 for alternative A1. And in our study, that is, for example, the installation cost in euros for A1. And you can just go ahead and populate all the rest of the values in that matrix. Once that's been done, we move on to the fourth step, which is normalizing the decision matrix. And effectively, what this does is it removes any influence of units or variables of significantly different magnitudes, and then scales the values based on the preferences defined in the weight vector. Once we have our weight normalized decision matrix, we can then calculate our relative closeness. And this relative closeness is effectively a measure of how close each alternative is to a fictitious ideal solution. And the largest relative closeness value indicates a solution that is the closest to the ideal solution. And then once you've calculated this value for each of the different alternatives that you're considering, you simply rank them by relative closeness from largest to smallest, the largest being your preferred alternative. So now that we've covered off our environmental impacts, life cycle assessment, and our multi-criteria decision making, it's time to combine all of this together and apply it to our case study building. So the case study that we're looking at is an existing school building located in Isola del Gran Sasso d'Italia in Abruzzo. It's a typical pre-seismic code construction from around the 1960s. This particular structure has 2 above ground stories and a small partial basement at the east end here. The first and second floors both have areas of approximately 630 square meters, and the primary structural system consists of 2-way reinforced concrete moment frames in both the longitudinal X direction and the transverse Y direction. There are also a number of unreinforced masonry infills and partitions present throughout the building, with large presentations in the exterior infills to allow for the presence of windows and doors. We modelled this case study building in OpenSeas following the recommendations of O'Reilly and Sullivan. The RC, or the reinforced concrete members, have been modelled as flexural lumped plasticity force beam column elements. The beam column joint elements have been modelled using a simple scissor model with the moment capacity of the central spring calibrated to represent the shear strength and the deformation in the beam column joint. And the infills have been modelled using a simple single strut model with stiffness and strength reductions to account for the effects of penetrations in the infill. As the structure is located in Italy, we've performed our seismic assessment in accordance with the provisions of the local design code, Norme Tecniche Costruzione. We have a class 3 structure with a 75-year nominal life, and we need to consider 4 limit states: life safety, or immediate occupancy, damage limit state, life safety, and the collapse limit state. And the elastic design spectra corresponding to each of those limit states is shown in figure 12 here. And additionally, there are a number of verifications that needed to be performed at each limit state, such as global displacement checks on interstory drift, local deformation checks on our elements, and also strength, demand, resistance checks as well. Those are all summarized in table 2 on the bottom of this slide. We carried out an initial seismic assessment of this as-built structure using a displacement controlled pushover analysis with a first mode shape load pattern. We then use the N2 method to determine the performance displacements at each of our 4 key limit states. You can see on the right-hand side an indication of the drift profiles at each of these particular limit states. And you'll see that the as-built structure has acceptable drift performance, given that at the immediate occupancy and the damage limit states, the maximum interstory drift is significantly below the code specified limits. On the other hand, if you look at the left-hand side, you'll see that the shear capacity of the beam column joints down here and the shear capacity of the columns are exceeded well before we reach displacements corresponding to the life safety limit state. And additionally, the infill strain associated with immediate occupancy occurs prior to attainment of the immediate occupancy limit state. So these are the 3 main performance characteristics that we're going to need to address when we design our retrofit solutions. So the retrofit schemes that we developed for this, we developed 5 for this particular case study. The first alternative, A1, uses carbon fiber reinforced polymers, and it's an example of local member strengthening that's been designed to improve the strength hierarchy of our beam column joints. Alternative A2 utilizes a cheap retrofit alternative that utilizes concentric steel braces applied to the exterior of the building in select locations. A3 is effectively the same as A2, except we've included carbon fiber wrapping around the columns, beams, and joints to increase the local capacities. With A4, we've attempted to reduce the seismic demand on the structure using a series of viscous dampers and also increasing local member capacities with FRP. And then finally, alternative A5 uses reinforced concrete shear walls, joint enlargement using a post-tension steel angle system, and small amounts of FRP to improve local member performance. A retrofit measure that's common to all of these retrofit alternatives was the separation of infills from the surrounding frame in order to prevent any infill frame interaction from occurring. And these alternatives were designed using an iterative design procedure where failing elements were identified and retrofitted, and then were reassessed to determine how the new structural properties would affect any other elements. Once the structures were designed, we performed an initial seismic assessment in much the same way as we did for the as-built structure. And some of the main trends that you can see from these pushover curves is that particularly in the X direction, you see a reduced stiffness, a reduced initial stiffness in the retrofitted structures. And this is obviously a direct result of providing a seismic gap between the infills and the reinforced concrete moment frame. Some of the advantages of this reduced stiffness is that it's likely to reduce acceleration demands on the structure, and that will have flow-on effects, hopefully leading to reduced losses of related to acceleration sensitive components. And you'll also notice you may notice in these plots in the middle here at the life safety limit state that the beam column joint shear capacity is exceeded for alternatives A1, A2, and 3 because we were not able to meet the code requirements for strengthening using a practical amount of materials. Now, this basically means that these particular retrofit alternatives are not strictly code compliant. However, this is not such a big issue because you'll notice that there is still a significant improvement compared to the as-built structure. And this sort of thinking is in line with the thinking behind recent government retrofit guidelines that have been issued in Italy, such as Sesma bonus, which they basically encourage retrofitting on the basis that any level of improvement to your structure is better than not retrofitting at all. So on that basis, we proceed with these 3 retrofitting solutions, even though they don't strictly meet the criteria specified in the NTC design code. We just take a quick look now at the drift profiles, and as you would expect, the lower stiffnesses, the lower initial stiffnesses seem to have resulted in an increase in the displacements. However, this is not really an issue given the fact that for the most part, they're generally still below the limits at the immediate occupancy and the damage limit states. There's only one case where one of the retrofit solutions exceeds this limit, but you'll see later when we perform our nonlinear time history analyses, it's verified that the drifts are actually much, much lower. So, talking about our detailed seismic performance assessment, we performed it in accordance with the PAIR PBE framework. We started with our multiple stripe analysis. We had 10 stripes with return periods between 30 and 2,475 years. We selected our records using our average spectral acceleration on a range between 0.05 seconds and 1 second. And we obtained our records from the Engineering Strong Motion database. And you can see the acceleration response spectra for each of the 4 limit states shown in the bottom right corner here. There should be 20 records for each stripe. The next step is our structural analysis, and you can see the key results from the analyses in these 2 figures here. The figure on the top right shows the collapse fragilities from our multiple stripe analysis, and they've also been modified to account for different modeling uncertainties following the recommendations of O'Reilly and Sullivan. In this particular study, collapse was considered to have occurred when either the shear capacity of the beams or columns was exceeded, the rotation of the plastic hinges of the beam, column, or wall elements exceeded the collapse limit state limits, or the rotation of the beam column joints exceeded 0.02 rad. And you can see from this figure that the median collapse spectral acceleration has increased for all of these alternatives, particularly for A3, A4, and A5, where in some instances the median collapse capacity exceeds 1G. The figure in the bottom shows the maximum peak floor accelerations, peak floor velocities, and peak story drifts obtained from our nonlinear time history analyses, plotted against a return period. And as expected from our initial seismic assessment, you can see that the peak floor accelerations here have been significantly reduced compared to the as-built structure, and this is particularly obvious for A1 and A4, which have reduced demands due to the increased flexibility for A1 and the increased damping associated with A4. In terms of the peak story drifts, you can see here that the drifts tend to be a little worse, particularly in the X direction compared to the as-built structure. However, they're still well below the 0.33 and the 0.5% drift limits at the immediate occupancy and the damage limit state. The third step in our PAIR PBE assessment is developing our inventory of damageable components. In this particular study, we used the PAIR Performance Assessment Calculation Tool, or PACT, to develop our component inventory and perform the necessary performance assessment calculations. The types of components and quantities that we used in our structure were based on data from previous studies, which drew from in situ surveys of typical Italian school buildings. In terms of our sources of fragility data, we either adopted data directly from PACT for components that already existed in the PACT database. And for those that weren't already in the PACT database, we were able to obtain fragility data from existing literature. In terms of repair cost estimates, we were able to convert repair costs from PACT US dollars into Italian euros using the PACT to euro conversion method described by Silva et al. In their recent paper. For structures that weren't in the PACT database, we were often able to obtain our repair cost estimates directly from the literature we obtained our fragility sources from. And for the likes of contents materials like bookcases, computers, desks, chairs, things like that, we based our repair cost estimates on expert opinion. In terms of our environmental impact estimates for components located in the PACT database, we were again able to use the environmental impact estimates from PACT. As a recent update to PACT has included these in the database, and they use the same economic input-output life cycle assessment database that we use for our calculations. For components not already in the PACT database, but have similar repair requirements, we were able to estimate the environmental impacts by scaling the environmental impacts of similar PACT components on the basis of cost to obtain a suitable environmental impact estimate. And then our third method for calculating our environmental impacts was creating our own cost estimates and then using the calculation procedure that we've discussed previously, and you can see here in this figure. The final step of our detailed seismic assessment is our loss and environmental impact analysis, the results of which are shown on the slide here. The top figure shows our economic and environmental impact vulnerability curves. And if you take a look at these, the first thing you can see straight away is that our as-built structure A0 is extremely vulnerable, and collapse plays a significant role in the losses. And you'll see also that A3, A4, and A5 show a significant improvement over the as-built structure and even A1 and A2. And that is a direct result of the superior collapse performance that we highlighted in the fragility curves a couple of slides ago. In terms of the expected annual losses, the as-built structure had an expected annual loss of 0.5%, which is in line with the results of other studies on similar structures. And all of our retrofitting solutions show an improvement in terms of expected annual loss, with our A4 showing the most significant reduction of up to 88% in the value of expected annual loss. And at the other end of the spectrum, A2 only reduces the expected annual loss by 14%. You can see an interesting thing to note here is that there's a almost one-to-one linear correlation between the expected annual loss and the expected annual environmental impacts of repair. And this is, we believe, the direct result of the linearity assumption of our environmentally extended input-output lifecycle assessment methodology. Now that we've completed our seismic assessment and got that out of the way, we can start with our selection procedure and attempt to find our optimal retrofit solution. The first thing we need to do is to populate our decision matrix with the values specific to each alternative. And our decision matrix contains four different types of values, which you can identify by the different colors in the figures at the top here. We have values that we're able to obtain directly from the literature, or to be calculated from values directly in the literature. We have values that we're able to determine directly from our structural performance assessments, values that we can calculate directly from our life cycle assessment procedure. And then finally, we have a qualitative values that we can calculate using or estimate using the analytical hierarchy process. And effectively, the analytical hierarchy process derives a quasi-weight vector that we can use to compare the different alternatives at each of these decision variables, and then we can use the values of this weight vector as inputs into our decision matrix. And you can see the results of the decision matrix here in this bar chart. You can see the values have been normalized by the largest value in each category. You can see also that there are clear differences between each of the alternatives. If you take A2, for example, which is shown in red, the low costs for installation, maintenance, and duration, and low need for specialized labor tend to be offset by the very high intensity-based losses, and also the expected annual losses and expected annual environmental impacts. Conversely, A4, which is shown in green, has relatively high architectural impact and installation costs, but it has very low intensity-based losses and expected annual losses as well. An important thing to keep in mind here is the differences in values for each of the three different environmental impact decision variables. So that's the installation environmental impacts here, the expected annual environmental impacts, and the environmental impact life cycle performance metric. In this study, we performed a total of 6 different MCDM assessments, each with a different combination of decision variables, so that we can investigate the effects of considering different environmental impact variables. Our 6 assessments were divided into 2 sets. Set 1 has 4 different assessments in it: DA, DB, DC, and DD. DA is effectively our baseline study, in which we don't consider any environmental impacts. We only consider typical social and economic variables. And for each of DB, DC, and DD, we consider different environmental impacts. So the installation environmental impacts, the expected annual environmental impacts, and our life cycle performance metric. And then in set 2, we investigate what effect a single aggregated economic factor has on the selection of an optimal solution when you use it to replace the individual installation costs, maintenance costs, etc. Now, the values of the weight vectors assigned to each of the alternatives is presented in this table, and it was based on the results of the survey that I mentioned earlier, and the weight vector from that survey is shown in the plot below. If we perform all of our decision matrices, our decision assessments, we arrive at, with this table here, which is the main result of this study, and it summarizes all of the rankings resulting from each one of our assessments. You'll see, if we look at the results for set 1, that alternative A2, the concentric steel braces, is the preferred solution when we don't consider environmental impacts. And you'll notice that when we consider installation environmental impacts, you'll notice that the preference for A2 to be ranked in first place is actually increased. Now we can tell that by looking at the value in the brackets. The value in the brackets is the relative closeness. And if you recall from our previous discussion, the relative closeness tells you effectively how close you are to the ideal solution. The bigger the number, the closer you are to the ideal solution. So if the preference is increased when we have installation impacts, we see the opposite occurring when we use our life cycle performance metric. And in fact, the preference for A2 to be ranked first is actually reduced. And then if we use expected annual environmental impacts as our decision variable, we actually see a significant change in the rankings. And in this particular case, A2 is kicked all the way down the rankings to number 3, and our preferred solution becomes alternative 3. Now, given that the weight vector is the same in each of the 3 assessments, including environmental impacts, the difference in these rankings and the strength of these preferences is that must then be associated with the actual values of the decision variables for each of the alternatives. And that's actually quite easy to see when you look at this plot of the decision variables. A2 has by far and away the lowest installation environmental impacts. So it makes sense that when you include a variable where this alternative performs favorably, of course it's going to strengthen the preference for A2 to be ranked first. Conversely, A2 has the worst performance when you look at your expected annual environmental impacts. And as a result, you see a change in the rankings with A2 being relegated down the rankings. And the environmental impact lifecycle performance metric is somewhere in the middle. So you can see that A2 performs worse than A3 and A4, and that's why we see the preference of A2 being reduced. However, you'll notice that the gap between A2 and A3 is nowhere near as severe as it is for A2 and A3 in the expected annual environmental impacts. And as a result, we don't see that dramatic change in the overall rankings. So what this tells us is it basically highlights the fact that it is important that you make an appropriate choice of your environmental impact decision variable when you're performing one of these assessments. In general, it would be recommended that the life cycle environmental impacts, or in this case, the life cycle performance metric, would be the sort of the go-to variable. It's definitely the most comprehensive because it encompasses environmental impacts from the entire life cycle of the structure. However, that being said, it can be a little bit tedious to calculate, and you do need additional knowledge of life cycle assessment to be able to do that. However, the expected annual environmental impacts are much easier to estimate, particularly given that the majority of the required data is already available in software packages such as PACT, and you simply apply it through the performance-based earthquake engineering methodology, which is well known to many of us earthquake engineers. And the results of these rankings show that using the expected annual environmental impact alone may not actually be a terrible alternative, particularly if it makes it easier for users to consider environmental impacts in their analyses. Because in this particular instance, it severely punishes A2 for its poor performance, but A3 and A4 remain the sort of the best alternative outcomes in this situation. And given the fact that when you consider the environmental impact life cycle performance metric, the results from the DC assessment, A3 and A4 are actually not that far behind A2 in terms of their relative closeness values. So the outcome of using the expected annual environmental impacts is not really that bad. This finding is obviously situation specific, and you should keep in mind that if you're going to do this, potentially more research needs to be done to verify that this actually is an acceptable assumption to make. But it's definitely, from the findings of this research, look like something that could make it easier for more people to include environmental impacts in their decision assessments. If we take a look across both sets now, set 1 and 2, you'll see that there are a number of cases where the inclusion of the environmental impact decision variable has little practical effect on the rankings. It basically has no change to the alternative ranked in the first place. And this actually does beg the question of, is it actually, like, do we need to include environmental impacts in our assessment? Like, they don't appear to change the alternative ranked first much at all. And the answer to the solution actually depends on a couple of factors, those being namely the dispersion of the values of the environmental impact decision variable between each of the alternatives, and also the weights assigned to each of the decision variables when you define the weight vector. So talking first about the dispersion of the decision variable values, when you use a relatively uniform weight vector like we have in this study, and you can see that again in the top right corner shown by the dark blue bars, when you have a weight vector like this, the variation in the values of the decision variable need to be large in order to affect some sort of change in the rankings, because of the sort of the averaging effect you have of the very sort of uniform weight vector. And you actually see this happening in this particular study when you compare the difference between DC, the life cycle performance metric, and DD, the expected annual environmental impacts. You know, we talked about the difference between A2 and A3 before. In here, it's much smaller than it is over here. And that's effectively what causes one of the changes. So that's one thing to keep in mind. The second factor, and probably the most significant of the two, is the value of the weight vectors. So the weight vector tells us, like we mentioned before, the relative importance assigned to each decision variable. And it was a key observation from some previous work that our group has done, that of all of the sources of uncertainty and the values that you can tweak in a multi-criteria decision-making procedure, the one that has the most significant effect on a ranking change is the values of the weight vectors. And we can actually illustrate this effect by comparing the rankings obtained from two weight vectors with very different shapes. And you can see those in the top right corner here. We have our uniform weight vector, and we have a much more jagged weight vector that we obtained from a recent study by Gentile and Galasso. Now, in this particular comparison, we don't specifically look at environmental impacts, but for illustrating this point, that's not really too important. And you can infer what would happen if you were to change the weight of, say, the environmental impact in our particular assessment. So if you perform your decision assessment using these two different weight vectors, then you get some rankings that look like the ones shown in the table on the bottom of this slide. And obviously we have a different set of rankings between DA and then those obtained from Gentile and Galasso. And you also notice that there's a change in the strength of the preferences and the spread of the relative closeness values as well. And what this indicates is that it is the preferences of the decision maker that have the most impact on whether or not the inclusion of environmental impacts will alter the rankings. In addition, this also further highlights the utility of this multi-criteria decision-making methodology and its robustness and ability to adapt to different scenarios or the different priorities of a decision maker. And with that, that pretty much wraps up our study. Some of the main conclusions that you can draw from our work is that the environmental impacts of retrofit installation, maintenance, and seismic repair can all be determined using the environmentally extended input-output life cycle assessment. We have shown that the selection of an appropriate environmental impact decision variable is important and can have an effect on the rankings of your retrofit solutions. And we've looked at using the expected annual environmental impact as a simplified alternative to the total life cycle environmental impacts. And this could be a possibility, although further studies need to be conducted to verify that it is a consistent finding across a range of different types of structures. And we've also illustrated that the most important factor in determining the influence of the environmental impact decision variable on the rankings is the weights provided by the decision maker. In terms of future research, we're currently looking at extending this work by using this framework to find optimal combinations of seismic and energy retrofitting measures. So instead of just looking at the embodied environmental impacts that I mentioned way back at the start of this presentation, we're going to expand it to include the operational impacts as well. And we're going to look at how we can retrofit existing structures to improve their thermal performance and energy efficiency, and then how we can combine the effects of these two different retrofitting solutions together to incorporate them into this multi-criteria decision-making process. So that's everything that I have to talk about that. Now you guys are more than welcome to ask me any questions you like. And if you want to know a lot more about this topic, then you're more than welcome to get in contact with myself or any of the rest of the team. I just want to say thank you very much for both your time and your attention. Thank you.
Okay, so thanks, Nick, for a very thorough presentation. You had, I think you were just slightly over time, but it was very well presented and very well explained. So well done for that. Do we have any questions or comments for Nick on the work he's presented? Anything you want to ask or clarify from the audience? If you don't want to ask, you can also write in the chat. I see that Gabriele Guerrini has raised his hand. Go ahead.
Yeah, just a curiosity. First of all, congratulations for your work. It was a very interesting presentation, so thank you. And really, it's a curiosity mine. I think it was on figure 7 of your presentation. It was quite at the beginning, if I remember well.
Yeah.
And it was, I think, on the, yeah, exactly here. So I just didn't understand why in the parameters that affect the impact of the retrofit installation, there is nothing related to construction like transportation and labor. Like a retrofit, such as inserting shear walls or brace frames within an existing structure, may require some relevant construction work. So I didn't understand why it was excluded from there.
Certainly. So in this particular case, in terms of construction materials, so if you're inserting a reinforced concrete shear wall, all of these sort of the materials that are involved in that, so the concrete, the steel, the plywood for the formwork, etc., that's all of those particular effects are, and the impacts associated with those are included in the raw material and the material manufacturing. So by the time you get to the end of the material manufacturing stage, you have your reinforcing bar and your ready mixed concrete and your plywood sheet. And then the actual construction phase is just putting those together to create your wall. So a large portion of that is involved as human labor, and human labor is not typically considered in these impact assessments, primarily because humans typically themselves don't typically emit a large number of noxious gases or anything into the environment. Transportation, though, is a very good point, and I touched on that in the presentation. Is we chose not to include it in this particular study because it can be quite technical to work out the actual values, because it's all based on transportation routes and the type of vehicles you're using. It's very detail specific to be able to calculate it. Yeah.
I see, but why would you include them when you evaluate building replacement then? Because
yeah, sure. So the reason that we do that is the way. So when I was calculating the repair estimates and the installation costs, we had a very detailed itemized list of all of the materials that were going into our particular repair options. And when I look at the total replacement cost of the building, we made a very rough calculation, because in our input-output industrial sectors, there is an industrial sector titled which encompasses educational and vocational buildings, and it effectively says when you construct a building for $1 of construction, of $1 value construction of this building, what the environmental impact of that is. And of course, we could, by applying our reconstruction cost and multiplying it by that corresponding impact value, you get that impact factor. But because the industrial sector, that particular industrial sector includes because it's related to a finished building, a dollar value of a finished building. When you have a finished building, you've already accounted for things like the transportation and the labor in constructing that, and that's accounted for within this within that system. So that's the only reason why it's included in that particular thing. If we wanted to, we could have gone through and we could have itemized every single thing in a building and done a more detailed case and a detailed estimate of our impacts associated with replacement. And in that case, we would have had the same assumption as the other repair estimates and retrofit installation, and not have any effects associated with transportation and labor.
Okay, thank you very much.
Cool.
And again, congratulations.
Thank you very much for your question. Thank you.
Okay, thanks, Gabriele. We have another hand raised from Daniel. Daniel, go ahead if you want to ask.
Hi, yeah. Thank you very much for the very interesting presentation. I had a question about the design of the retrofit schemes. So how did you make sure that the retrofit schemes are comparable, let's say fairly comparable? Because maybe for one retrofit scheme, if you apply much more material, you can achieve a much better performance compared to another. So how did you kind of balance out the different retrofit schemes?
Yeah, okay, yep, it's a fair point. So effectively what we tried to do is we effectively tried to meet a sort of a minimum level of requirement. So basically, I said we had our sort of iterative procedure where we were trying to, we would assess our structure, we'd identify the elements that were failing, we would retrofit them, we would apply a retrofit solution until those particular elements were no longer our elements that was controlling sort of our failure or controlling our performance. And then we stopped improving our structure once we got above our specified performance point. So all of the structures have had effectively the minimum retrofit done to them to prevent any of the elements from having capacities lower than the required demand.
Okay, thank you.
Yeah, no problem.
Okay, anybody else, anything to add or ask?
Gerard, I would like to ask something.
Hey, Karim. Yes, sure, go ahead.
Nick, thanks a lot for the interesting presentation. I have a few questions, pretty simple, but I was just curious about them. So first of all, you said that when you designed the retrofitting in a specific panel, you assume that the infills are isolated from the mainframe. You mentioned something like that, but I didn't get it exactly. So could you please elaborate?
Yeah, sure. So effectively, in this particular case, we looked at, we noticed that you have, sorry, I'll start again. When you have unreinforced masonry infilled frames, you typically have infill frame interaction, in which case the infills can induce quite significant shear forces in the columns. And in our particular modeling situation, we just modeled our infills with a simplified strut model, a single strut model going from centerline to centerline of our beam column joints. And that's not able to capture effectively our infill, our frame infill interaction. And when we retrofitted our structure, we wanted to avoid any detrimental effects sort of associated with this interaction. So effectively what we did is we provide a small seismic gap around between the infill and the moment resisting frame. And then you make sure that that gap is big enough that when the structure drifts to its collapse limit state drift, it's not going to close up that gap and then have the interaction between the frame and the infill again. In terms of, obviously something that you would need to consider is that if you separate the infill from the frame, you're then going to have to deal with some sort of somehow deal with the out of plane effects of the infill. In this particular case, we didn't address those specifically. We were only really concerned with the in-plane performance of the infill, but you could potentially fill the gap, the seismic gap, with compressible insulation materials. You could apply sort of fiber reinforced plasters to help improve some of your out of plane performance of the infill as well. But we didn't specifically look at that in this study.
Okay, yeah, I got it. Now, I understand that your retrofitting process was like, okay, you see how the elements are performing and you do the retrofitting based on that. So if you got some elements that need retrofitting and you isolate the infills in that location, you might actually create additional problem in your structure. Like, okay, the infills, I noticed that they are uniformly distributed. If you remove some of them or you consider that there is a gap, you might create a soft story or some sort of concentrated demand in that particular location. So when you were doing retrofitting, did you apply it in the whole floor in this case? And you assume the whole floor is, the infills are isolated from the main frame, or I didn't get that, to be honest.
Yeah. Okay, fair point. Yeah, so you're correct in that if you isolated the infills in specific locations, you would induce some pretty strange effects within your structure, I would imagine. In our particular case, we assumed that all of the infills were going to be isolated, separated from the structure.
Oh, okay.
Yeah.
Now,
so once we've retrofitted it, it effectively becomes an unreinforced moment frame that you then retrofit. Yes.
Yeah, I got it.
Sorry, I could have been clearer about that. Yes.
No problem. The last question is the time that you apply because you said that when you apply retrofitting, it's like a separate life cycle. Didn't you say that, if I'm right?
It is yeah, to some degree, it is a separate life cycle as well. So like when you apply a retrofit alternative, you have to consider the material acquisition, the raw material extraction, the material manufacturing, construction, and then also potentially maintenance requirements associated with the retrofit installation as well. Yes, so it has its sort of own life cycle.
So in this case, if the school that you're retrofitting is like 1 year before the end of its service life, and if you apply retrofitting in that case, it means that you're starting another life cycle, a complete life cycle after retrofitting. Is that what you assumed?
Starting a complete life cycle? No, because a building doesn't restart. You wouldn't say the building restarts its life cycle. When you retrofit the structure, you can say that you are sort of extending its. You're likely to be extending its useful life. I mean, you're not going to typically retrofit a building if you're going to take it down in sort of 5 years' time. Basically, effectively, you can see in this figure here that it's kind of like when you retrofit the structure, you effectively have kind of like a side branch of life cycle phases that then feed in to the main building life cycle, which is this main one at the top here. And this use phase can be as long as you need it to be. I mean, expected building lives are really just a number. I mean, the building will stay around for as long as people have use for it, and retrofitting it and extending its useful life. Yeah.
Oh, okay. Thanks a lot.
Yeah, no
well
problem.
Done.
Thank you very much for your comments, Karim.
Okay, so I think we're a bit over time, so we may have to leave it here. Both Professors Calvi and Montero said they had to leave, so but they just wanted to pass on the messages of well done. So so yeah, we can maybe leave it here. As I was saying before, I've been recording this, so we'll be putting this online at some stage later on this evening, so it will be available for anybody who maybe has missed it or would like to see something again. And apart from that, I would just like to say thanks again to Nick for a very nice, thorough presentation. I think you went into everything in very good detail, and also to everybody for taking part and for the questions and comments and just general discussion. Okay. We'll try to have maybe a few more of these seminars online, so maybe just stay tuned. We'll have some links or some further things coming in the near future, so we'll hope to see you all again soon. Okay.